G'day, I'm Glenn Morris from the Smart Energy Lab, and today in the lab I've got Dan Su from Jinko. We're going to get kind of geeky about solar panels and solar panel technology, aren't we?
Yeah, that's all we're here.
And look, I've rearranged the studio a little bit, and we've got some of these beautiful Jinko modules behind us. These are the Tiger Neo N-types. In fact, these are the big ones, the 430 watt models. But we're going to talk about the product in general, and it comes in a range of sizes, doesn't it?
Yeah, no, I'm actually going to correct you straight away. They're not the big one. They're the smallest one we have now.
Are they?
Their power, is bigger in the power, but keep in mind, they're much shorter right now, right? So we're looking at only 1.7 meter tall.
Yep.
Yeah, of these panels. So it's pretty amazing. Like, yeah, when we're thinking 400 watt,
yes,
straight away think of, it's going to be too big, 200 meters, and tell people, hey, it's actually 1.7. They're quite amazed. Yeah. So think about how technology has been changing.
So this data sheet's now redundant.
No, it's 415 watt.
Wow. Okay.
But look at the size. It's actually 1.7 meter.
Whoa.
If you haven't realized.
Right. Yep. So I'm looking at them now. I see 1.722.
Exactly.
Yeah. I carried them in, and they are getting kind of heavy. So I think solar panels now are really a two-person carry.
Yeah, well, we try to keep it as low as possible. They are getting slightly wider. That's why you're looking at around 22. So it's 22 kilo on these things. But that's an average, approximately around 21 to 22. We do have a design target, for when people carry to be kept under 25 kilograms. So that's what we're heading to. Yeah.
But realistically speaking, in the construction industry, there are many things that are a bit heavier than 20 kilos. I mean, carrying timber, carrying sheets of plywood. Yeah. I think we've just been used to panels being small. I mean, I started in this industry in 1991, and the panels I put on the roof of my house were 75 watts, and I could tuck them under my arm. They're that small.
I know. Handling has always been an issue.
Yeah.
Well, I've done like engineering before, project management for rooftops, for solar farms. So really, when people handle is quite essential for rooftop. Like, you don't want to use heavy equipment. You don't want to use a scissor lift to get on the 2 stories. So how I just see installer just hold their panels like that, right, and just start to climb the roof. It's a bit crazy, but so we understand how important for people to to have it light, but also considering it's being compared to the 370s, 330s, right? It's a similar height, slightly wider, 2 kilogram extra, but you do got 50 extra wattage, which means for every installation 6.6 kilowatt, you can save, it's 2-3 less panels per installation. Well, I think it kind of makes sense.
Yeah. I think we've come to a tipping point, excuse the pun, that carrying things on your shoulder are not a great idea.
Well, it is. Well, we have in the past tried a lot of different sizes. Yeah, I think that's something we can talk about, how the modules, why are we looking at the size at the moment, what's being really changed in the difference. We can have a look at these smaller ones later on, but basically the cell size of difference are changing. The 330 has always been the perfect size, right? People love it. That is what we call the 158 millimeter cell size, so 158 by 158 of a square, and you either cut it half or just as a full cell. You're making the module, it gives you 60 modules per cells in a straight row, so it gives you that particular size, right, height and width. But now the cell size are getting bigger and bigger. Of course, the reason behind it is trying to make it cheaper, right? So at the higher string of supply, we need to have the polysilicons to be. We are now capable of cutting the polysilicon into a very, very thin level, right?
Oh, very thin.
Very, very thin.
How thin?
I think it's 0.5 nanometers. Like, forgive me, I'm wrong. This I may be wrong. I have to double check. Yeah.
Or, no, maybe not nanometers.
No, millimeters.
Micrometers.
This I have to check.
Nanometers would be transparent.
Yeah, that's right. I'll be talking about quantum levels.
Yeah. So basically, the p-n junction is really only nanometers thick. So the rest of it is just material.
Exactly.
So you cut it as thin as you can. It still performs the same.
That's right.
Yeah.
Yeah, so because we're always looking at, kilowatt per meter square. So our efficiency is per meter square. So yes, theoretically, the bigger the cell, it's more economy. But of course, you have to looking at the challenges of how to design into a module, right? We can actually make 220s, 230s. We can make 300 mil of cells right now. But is that really make sense? Is that really helpful to have them install or put it into the panel? And how difficult to do it? Manufacturing is also a big challenge of engineering. So at the moment we're looking at from 185 to now 163. That was last year. And now we're looking at 182.
These are millimeters.
210. So they're millimeter of cell size.
Of a square cell.
Of a square cell.
Right.
Yeah. And then you either cut it half or cut it straight. So there's a few ways to do it.
And the modules behind me, what size cells are those?
So these are the 182.
182. And the really big ones are that you're often used in the utility scale. What are they?
For Jinko, we still 182. It's just different size.
Different size.
Different
Okay.
actual cells.
All right.
Yeah. So we do have. There is another design in the industry which is 210.
Yep.
But of course, we're looking at how to balance into actual modules. They have good design. They have some bad design. We have bad design as well. So it really depends on the situation. It depends on how do you fit on the roof. So far, this is what we found a better solution for people who like a smaller module. We also have what we consider as a maximum size for domestic rooftop is this 470 watt. You have it outside.
Yes.
Which is 1.9 meter already for the same size, 24 kilogram. I agree with you. It's probably really need a very strong guy to carry it.
Or girl. In fact, my other electrician's a woman, so she was the one who installed them. Yeah.
A very strong person.
Yeah, right? Good.
So, but yeah, like if possible, it's always a 2-people job. But it makes sense. Like people want to have less installation. They want to do as much as possible in a day.
Yes.
Right. So, and especially given the weathers, especially like you only have a half a day a lot of times.
Yes.
So, one less panel sometimes just makes a lot of difference.
I think we've got a new problem that's sort of coming to the fore in Australia particularly, or at some extent in New Zealand, is the current rating of the panels are getting so big so quick that inverters aren't keeping up with them in terms of their input current ratings.
Yeah, that's a side effect of going a bigger cell.
Yeah.
Because obviously your current and voltage are depending on those size of the cell.
Yeah.
The voltage is more about how many you put in a string. The difference are pretty limited. So, but the 54 cells, 60 cells, 70 cells in a series, they just add it up for sure. But the current is really determined by how big the cells is. So 182 cut it half, you get something around 13 amps. That's the average you will be looking at. So we do keep talking to these manufacturers or these inverter guys. They're aware of the issue. They're catching up. I think so far it's okay. We see how a lot of the industries are catching up.
Yeah. So I'm just checking on the data sheet for a minute here. So these 430 watt modules behind me, their IMP is 13.49 amps.
That's right.
And they actually have a short circuit current at standard test conditions of 14.23, which is the number that installers need to use when calculating maximum current inputs times the safety margin, the 1.25 times safety margin. So that puts you up to around about 17.8 amps on the MPPT. It's pretty high, but there are inverters that can take that. It's just that the module current's been racing ahead, and inverter manufacturers probably haven't realized it.
Yeah, it's unfortunate of how which part of the industry is really driving it.
Yeah.
Right. So in the long term, at least in Australia, domestic is always the dominating.
Yep.
We do see a lot of utilities being picked up recently, like Jinko has been picked up a lot of utility projects. However, globally, the big utility is what's really the driven factors to pushing for bigger modules, to pushing for less LCOE. We talk leveraged cost of energy.
Yep.
Right. So that's kind of the reason the technologies are changing so fast, right? And it's not really a problem for other areas. Unfortunately, it's not really a problem for center inverters, for example. It is a challenge. There's still engineering problems to solve it. But it gives you more benefits of having a high current. And you think about bifacial panels. Bifacial panel will easily give you 17 amps, 18 amps, right?
Yeah.
So
with a good albedo.
But it's energy, right? You want these energies to make your return of investment. That higher current is something the whole industry need to work up together, especially for the string inverters. It is a challenge for everyone. But just to point out, the 182 is kind of at the moment is an industrial standard globally.
The 182 millimeter cell
yes,
size.
We're looking at 72% of global market share is sold as 182. You still have some 210. You still have some older gens. In China, the Chinese market, read the news last week, it's 82%. It's 80% of market share is this 182. So it is definitely a direction, but of course, we as a manufacturer, we're also awareness of these issues.
Yes.
So the later products you're seeing, we still try to maintain within that 15 amps of limit, at least for domestic products.
Yes.
I think other manufacturers are doing it, because if you see the utility products, you will see 18 amps or 17 amps. But anyway, when you have a bifacial, all of these could potentially going much higher.
Yes.
Yeah, so it is a challenge for string inverter manufacturers, but I know a lot of them are working on it, and they're quite success. They have upgraded a lot, so yeah, it will get there. It's always that.
Now, I've got a bit of a basic question here, really, about P-type and N-type cells. Now, for those in the audience who are not familiar, that a PV module or a PV cell is made up of a base material, which could be doped either N-type or P-type, and then there's a surface coating, which is the opposite. And that is the magic of a photovoltaic cell. The PN junction plus light creates electricity. But we basically had P-type for a long time, and now I'm starting to hear N-type, N-type, N-type. Why the change?
Well, I think P and N, they're not so different. They are very different. They're different slip of sandwich.
Yeah.
But it's all polysilicon, like I said, just different layers of their toppings.
Yep.
There are then benefits of doing an N-type, the benefits doing a P-type when we look at the bigger economical levels, right? So the first ever cells that made in Bell Lab is an N-type. So it's not, it's Asian technology. It's not new. But people just keep developing it. It's just like electrical car and fossil fuel cars, right? So it depends on which one is more economical, which one has the bigger industrial capacities to make. So in the recent years, we're hitting a bottleneck for the P-types. So if you're looking at the products for last 2-3 years, efficiency hasn't improved much. We have 19% to 20%, 21%. We kind of stopped there. That's because the PERC technology P-type have a limitations, theoretical cell limitations around 25%. And it comes down to module, there's a lot of losses, right? There's this cell to module losses. So you're looking at the module, even we have improved a lot through bus bars, improved a lot from, how do we design the module itself. But ultimately, you're looking at around 21%, 21.5% of cell module efficiency. For the N-type, however, you do have a better, theoretical limit of around 28%. So you can imagine how much we can do. Like we could possibly looking at in 2-3 years' time a 25% efficiency of a solar module, right? So on the same size, you could look at 500 watt, which is pretty amazing, and it is a target that we should be aiming for. But that's just one benefit, having more efficiency. The other efficiency, the other benefit, it will be the N-type compared to P. It has better losses. It has better characteristics against environment. So we know the P-types modules. There's LID, there's PID. So basically hot and humid, and the light inducing itself, it could start to harm the modules. You're looking at the warranty, you have the first year degradations. It drops the power by 2% and 0.7%, 0.6% every year to year. There's other ways to against it, such as gallium dopings. But it's kind of there. You can go as low as 2%, 1.5. However, for the N-type, just the example is you do not have that boron layers on the top, right? So it does not suffers from the boron oxidized issues, right? So when you boron oxidized, it creates. So the LID is when the levels being oxidized, it start to create a surface on the top.
Hang on. LID as in light-induced degradation.
So it is the kind of the highest issues for the p-types, right?
Yep.
That's alone leads to the 2% of degradations for the first year, right? That's why you have a higher degradation in the first actually 72 hours. But because of that's because of this boron oxidized level, you're just kind of blocking the light to go through. But for the untapped, because it's a flip-off sandwich, you don't have these issues. So the LID itself, you're almost as close as 0.5. This is kind of the test data we have seen in the lab. 0.18, 0.2, averaged out 0.5%. So it's compared to 2% degradations. We are now giving 1% degradation warranty for the first year, but in real life it can just do a little bit better. So all these losses and more power, it just make the economy more, make sense. That's all. Yeah. And given Jinko has pumping up the manufacturing capacity to a next level, we're basically switching all of our P-type capacity to N-type right now. So you have a big mass production capacity. It would allow you to make the cost even lower. So at the moment, the gap is very, very small.
Right.
To have this P and Ns is not as before we doing this as a premium products, we selling very, very expensive. Now it's more like it's very affordable, right? So it's like electrical cars. You have a Tesla, which is affordable. It's not a new technology. It's not a magic. But it was actually expensive. But now it's affordable, and then there's a market and there's a benefit for it. Right.
Wow. So in summary, the switch towards N-type gives you things like better temperature coefficient, better or less LID, and the price difference now is almost insignificant to P-type. So you've got a potentially higher efficiency target at 28% eventually. We're not there yet, but that's the theoretical limit.
Yeah.
I mean, it might sound small, being only 3% more than P-type, but when you think of it in terms of going from 25 to 28, that's actually a big step.
It is.
And, look, excuse my dodgy maths, but that's kind of almost like a 10% improvement.
It's a per meter square percent.
Yeah,
3% per meter square, which is quite significant.
And that's what brings the cost of solar down. Efficiency is one of the major factors, isn't it?
Absolutely.
Yeah.
Absolutely. Like, yes, you can have as big as panel you can. Like, we can make a 1,000-watt panel for 20% efficiency. Your roof won't be able to cover it. But yeah, you do want something that is high efficiency. It's more like you same body but different brand, right?
Actually, a 1,000-watt panel would only be 2 of these, really, or 2 and a bit.
Yeah, well, it could be a direction, but it's not. We can't think of a traditional way, right? So there are products out there which is pretty amazing. Those flexible ones. Yeah. It could be. It's a bit big, but it makes sense because it's lighter and it's more flexible. But they fit for certain scenarios. We more focusing on mass production, industrial level, not industrial level, but something more like a Toyota, right? So it's more accessible. I think that's the goal for that should be the goal for solar, to make it as cheap as the fossil fuels, and then we can start to take it over.
Well, I think we're there already with the price compared to fossil fuels, but there's another topic I wanted to get onto, which is really the construction of modules and things like bus bars. Now, I've got a couple of props. I think I'll just grab them.
Yeah.
So excuse me for a minute.
Yeah, it's a bit of history.
Here's a bit of history. So this is what 10 years ago, even less.
Probably less. This is a mono. Look at the colors. They're quite even. It's not a poly module. So it's around 2009, 2018, 17. Like we started introducing monofacial or mono technologies, switching from the poly ones.
Yeah,
it's a similar story. Like poly, mono. Poly is less efficient, but mono is more expensive. But when the industry start to catching up, they have more productions, there's more capacities. It start to driving the cost down, and then the mono start to become more sense because it's a better technology, right?
Yeah.
So, yeah, and you're talking about bus bar, which is very interesting. Yeah, so we had those 3 bus bars, 5 bus bars of technologies. They're driven by the cost. Like eventually, it's all driven by the cost actually.
So this is silver on here.
Yeah, so
This
the
is
silver
one of the
bus
more
bars.
expensive components in a cell is the silver.
Exactly.
Yeah.
So how to reduce the usage of silver while because it's a big shading on the cell as well, right? So how to minimizing the size of this bus bars is also a big challenge for the manufacturer. Like I said, we talk about cell to module level losses, right? 25% to 21%.
So the cell is without the grid on it. Basically, just the amount of energy that the cell can produce.
Exactly.
But you've got to harvest that. You put a grid on top of it, and now you're shading part of it.
Yeah, because you put it on grid, you start to shade it. You put a glass, there's losses to the glass.
Yep.
You know, you put the limitations, the other losses. You know, so these are also challenges. So improving it is also a direction that we have been working very fast. So I'm going to bring you the other ones. So this will become our last generation of, actually the first generation of N-type. So Jinko has been doing N-type. We started to the research and R&D in 2016. It's a bit history. We have first mass production products, the Tiger series. It was in 2019. That's around the time I joined Jinko, which is pretty exciting. You know, it's N-type products. First of all, we only have 80 megawatt of capacity at the time, so it's pretty limited. So this is what we look at, all black. Nice looking panels. Of course, this is a section of it, but you see a lot of innovations being used here. So these, you can see the bus bars. First of all, we found 3 bus bars to 5. So here's like it's 9, 10 bus bars. Those bus bars are much thinner than before.
Tiny. They're almost like the fingers. They're hardly much thicker.
That's thanks for the robotic, robotic and all these automations on the in mass productions. And you can see how, first of all, how thin is, and they're actually circular. This is special for Jinko. There's actually, so you look at the cross section of the bus bars.
Oh, they're circular.
Yeah, outside there are
for
square
current
ones.
carrying.
These are square ones.
Yes.
You have triangular ones. You have circular ones, right? So we decided to go for the circular one
So
because
less shading.
Less shading, and theoretically, you have a little bit of reflections in between those cell and glasses.
You're just ringing every single watt.
Yeah, we're just trying
cell.
everything we can, but that's just because the perk limit is hitting the bottleneck. Like I said, the cell efficiency are there.
Yes.
So trying to reduce the gaps of in between the cell losses into the to the module losses. So this is actually a way we're looking at it. It helps like by even 0.5 watt is a big deal, right? Just by doing this, and the other things you probably be looking at is you don't. It's not always the more the better, because yes, like I said, there's shadings and what's the size of it. So when we're looking at the latest technologies, it's become a 16 bus bars.
16
as high as 16 bus bars.
Huh.
We have a range of 12 and then to 14 then to 16. Yes, but they're much thinner than before.
Yes.
Yeah, they're very much more thinner than before.
Yes,
but it allows more current. It still allows the SMS current to go through. Actually, more current to go through. But also, less shadings. It all gives benefit, because if you have the same thickness cross sections, even increasing the numbers by extra, it doesn't really helps, right? It's not always helping. The other benefit is if you do have microcracks, during installation, which is unavoidable. Then it helps as well. You will have a cross being limited in these sections and not actually spreading out for the entire modules.
Oh, right. I never really thought about the fact that more bus bars reduces the impact of microcracking.
Yeah.
Yeah. So it's instead of if you crack across here, you're losing 1/3 of the cell. Yeah.
Yeah, exactly. That's another thing to think about, and you cracks leads to hot spots and everything.
Yep.
Yeah.
So one of the advantages of lots of very, very thin bus bars is that they're more tolerant of microcracking.
Yeah, that's absolutely, because if you crack in this section, you're basically limiting in that section. Your bus bar is kind of just block it in.
Yeah. It's kind of like microcracks is not something you want to happen though.
Yeah, it's unavoidable.
Yeah.
We be more tolerant on these things. Like when we say when we designed warranty, saying the modules 2% degradations, 3%, 1%. We're gonna have to account that there eventually will have some microcracks happening. You know, so you think about how the modules are being made. Is when they leaving the factory, we will take EL pictures. We'll take a flash test,
so
electroluminescence to making sure. So you will see if there's any cracks, if any shadowings, if any dots in those cells.
It's amazing. I've looked at those pictures of cracked cells, and it suddenly looks like someone's just smashed the thing to pieces, and then you see it in daylight and you can't see a thing. It just shows up all those faults really visually.
Yeah, exactly. But you can't say like everything is perfect, right? There's a tolerance level. So, for example, if it's just every cracks and dots, we have a certain criteria. So it shouldn't be longer than X centimeters. It shouldn't be bigger than X meters per square. You should have more than 20 or more than 10, something like that. So this will allow us, but this is just a tolerance, because we know when it goes through shipping, when it goes through installations, they will eventually have some microcracks. But don't be too worried about it. There are some tolerance building. Yeah.
I'm really interested in this. I'd always kind of thought of microcracks as must be avoided, but actually, if you design a module to be tolerant and not be potentially catastrophic failure as a result of a microcrack, because when you've got very few bus bars and a microcrack can carry the full current, it gets hot. And so you get brown spots, you get possible little hot spots that can even melt the fingers. But if you've got lots of bus bars, the current's very small, evenly spread.
We're not saying you should don't care about anything. You should be at all costs with precaution to not leading to more damage.
Yes.
Because what we see in the factory, sometimes we can let it pass because they're small.
Yes.
But on the sites, like especially if you put your hand against your helmet, it's actually causing bigger problems, right? So,
yes, I've told people have shown me electroluminescent pictures of modules, and you can see where the head was, because there's sort of radiating out from the head is the cracks, because they've carried it and flexed it like this.
Exactly. Yeah. What you might see is what we call snell trails.
Yes.
Right. So snell trail it theoretically doesn't affect, like, overall it will, if any microcrest, it will affect your powers.
Yes.
Right. But we do have extra powers in those modules. When we sell you a 415, they're usually being a 416 or 417, right? So there are some tolerance to have some issues in there. You lost the 0.1% of power. You're still meeting your target.
Yes.
But like I said, installer should be very, very careful when handling this. So handling is a big challenge for everyone as well.
Yes.
Yeah. It's an interesting topic when we talk about handling. Is there's one just about like how mistakes being made and being learned in the past. You see those modules. You notice. This missing the VC frame. It is one mistake that we have done in the past. We're kind of removing it because at the time we designed it bifacial panels that have less shadings to the back. So we removed it. But people don't realize is when you have such big panels, you need somewhere to grab it. Right? So removing the C frame is causing the problems of handling on the modules.
Yes.
So we actually learn from it. We bring it back, all of the modules.
Right. Okay.
So that's it's always been a journey of making some mistakes and coming back on these details. Yeah.
I mean, the other thing is that on the short side of the module, the C section has got smaller and smaller.
Yeah.
To the point where it's non-existent on some modules, which makes it difficult for clipping cables, because the little stainless steel clips that you push on, they need a little edge edge to clip onto.
Exactly. That's why like it's a learning curve for us.
Yep.
We had this removed for one time and we bring it back straight
All
away.
right.
Yeah.
Okay.
It's pretty interesting.
Coming back to microcracking, I should just point out to the viewers that we're not talking about the glass cracking. That's definitely the job's. It's all over. You basically lost your insulation. If the glass breaks and cracks, water will get in, and you've now got a hazardous panel. Of course, the inverter's going to detect that and raise an earth fault alarm. We're talking about the virtually invisible cracks that only with special equipment like electroluminescence are possible to see. But I'm really encouraged by the fact that you've considered that, because you might have the best produced panel in the world leaving your factory, but after that it's not in your control. It goes onto shipping, it goes out to warehouses, people pick it up with forklifts, it goes onto the back of installers' vans and trailers, bumps along bumpy roads, gets put on a roof, and then the owner can walk all over them, and then the person who comes to clean your roof walks across them. You just don't know what's going to happen.
Yeah, exactly. So what we're doing right now is every panels that have been produced will have EL images being saved in the database.
Oh, wow.
So it will be saved for like 10, for target to save it for 10 years, 20
every
years.
panel or just a sample?
Every panel.
Oh my gosh, that's
Every
a huge
panel.
amount.
It's a huge amount. For 100 megawatts of delivery,
Yes.
it's like gigabytes of data. I have to give you a hard drive. I just give you like, here's all the images. I'll put in the hard drive. I'll DHL send it to you. Like, it's just too big files to download. But you get a picture of every single modules. So there's very good traceabilities of new products right now. Like, we got serial numbers printed on every panels.
Yeah.
From the serial number, we will find the EL images. We'll find the original flash report.
Yep.
So what we can possibly do is 10 years down the track, you have find the big problems on your panels. You have hotspots. You have cracking, snail trails all popping up, right? Which, like I said, microcracks. If it's severe ones being hit by helmets, it could grow up into a hotspot. It could grow up into some other issues. We can scan them actually with the IR camera instead, right? It's probably easier to pick it up after the problem has been become, but we can always refer back to the original images and see sorry, there wasn't a crack at the time.
Yeah.
So it's possibly we can tracking down who's the responsible party it is. But really, from statistic, if a panel survive the first 2, 3, 5 years, like maximum 5 years, the rest of them is less impacted by workmanship. That's including manufacturer workmanship. That's including installation workmanship. So the rest of them will be just the materials.
Yeah.
Right. So if you have any issues with the installation, with the product qualities, usually it will show up in the 2 years. You got dial failures. You got micro cracks and sorts. Well, just being here long enough to understand all this, to try to improve ourselves using a lot of automations right now, keep improving the qualities. So we know these things can be avoided. Yeah.
So just touching on IR and electroluminescence, for the installers out there who want to say, how can I test that there's a fault with the cell, that the microcrack is bad, and it's then unlikely to have an electroluminescence piece of kit, which is very expensive, but an IR camera, I mean, these days I've got ones that plug on the bottom of my phone. They only cost like $500. Are they good enough to see microcracks?
They won't see the microcracks. Like I said, you will see it as a hotspot until the cell is actually this severe damages and start to, you will start to see a hotspot as a result of a microcrack.
Right. So you'll see a temperature difference, but you won't actually see the crack. That's good enough. Yeah. So one cell will be hotter than the next cell.
But even for the temperature, it's not always. It's hotter, it's bad, right? There's always a range.
Yes.
Our recommendation is 20% cell to cell, so 20 degrees to cell to cell. If one cell is 20 degrees hotter than the other, it's definitely an issue. If it's 10 degrees, about 10 degrees, then you should continue to monitor it.
Right. Okay.
Going bad.
That's a good tip, because for people who are not familiar with using IR cameras, often when you have them on auto range, they automatically go from what looks like red being hot to blue being cold.
Yeah.
Looking at just what they can see, so they always have things that look red hot and things that look blue cold, unless you know that you have to set the range.
Yeah. Right. You could see a very very shiny cell,
Yeah.
and you think it's a bigger problem.
Yeah.
But when you look at the temperature range, the hotter is 25, the
Yeah.
colder is 22. Then
Yeah.
it's
only
yeah.
3 degrees difference.
It's actually not bad. But I agree with you. Like in general, identifying troubles in a solar system, not just a module, in the solar system is difficult. Right? We've been looking after our customers. We do have a lot of calls, so my system is not producing. And unfortunately, a lot of installers being, gone, and we have often customers out there trying to looking after them. It's also become an issue how to identify it's a module issue, it's an insulation issue, it's it's a system overall, right? So I think a bit of the tips is we do find when you have an insulation issue, for example, it's the hardest one to define. Check your connectors, check your cables. That's 90% of the issue. Actually, people not fully inserting the connectors. If it's not pushing, so these plastics are not as flexible as your Legos, right? Even your Legos, right? Think about if you're doing a Lego. If
Have we got plugs
Legos,
on this?
Yeah. You play Legos, yeah. If you play Legos in an illegal way,
yeah.
it breaks. I tell you, like over time, it will break. It's the same issue. If you don't push it in fully inside, like it's very very secured. You get dust ingress, you got water ingress, and you will start to see troubles coming after.
I can't even put it in.
I don't know. These demos.
Oh, they're demos. Yep.
Yeah. See, I think it's this way.
Oh, there we go. Sorry.
Yeah.
Oh.
See that's the thing. Yeah, it's this way. So it will get in. I won't push it in. So
Because it's going to be hard to get
it'll be
apart.
hard to get apart. And
So
another
the
tip
problem
is,
could be that it hasn't been clipped in properly.
yeah,
Yep.
you really need to be fully insert.
Yep.
Have it fully relaxed.
Yep.
Also including the rubber bands.
Yep.
And then it's almost like secured, right? Otherwise, you could be looking at problems 2-3 years time. It will be very difficult to identify them. Yeah.
The other thing I've seen is people not tightening up the nut on the back.
Yes.
And so you can actually see daylight when you hold the between the wire insulation and the socket. The gland hasn't compressed fully, so
Yeah.
water's going to get in there.
Yeah.
But I've got a question about testing for earth faults. Installers often say to me, can I use my Mega to test for insulation on an array? Can you?
It's difficult. It's difficult. We had these questions a lot. We had installer tested them on the site. Unfortunately, it just doesn't give you a very good result. A lot of time we just let it settle. We give them freebies and close the case. But we do have tries to have them sending to the lab and do a wet leakage test. That's what we call it. So the panels will be fully merged into water.
Wow.
Right, while your connectors being so you connect them positive, negative.
Yep.
Your Mega is on the frame, negative on the frame, positive to both ends of them. So you test insulations.
Yep.
They're actually doing okay in the lab. They're doing quite good in the lab. But in the field, it's just so many issues, and it's very very difficult to identify. A lot of time they potentially are those connectors, and not being inserted fully, or could be a cable, could be DC isolators. I guess the only tips we can give them is making sure you're doing this right in the first time, and
that's more my question is, let's say you're doing an installation and you want to make sure that you haven't accidentally caught a cable between a rail and compressed it so that it's broken the insulation.
Absolutely.
Could you, down at the inverter, testing between positive and earth and negative and earth, do an insulation test?
If what you can do, yes, you can do it at section by sections.
Yep.
You can test the inverter first.
Yep.
You go to the string.
Yep.
Right. You should be able to identify which string at the inverter level. But at the string level, and then you move to the panels, it should be the last step. So from bigger to small, but it's very difficult because you could have one panel, yes, it have a cracker glass.
Yep.
So that's why I always recommend people to look visually first.
Yes.
Do you see crackings on the back sheet? Do you see crack in the glass? Do you see any damages on the connectors, on the isolators? If you find them, you're probably problem solved, right? So, but otherwise, it's going to be a bit difficult.
Yeah. Yeah, it's just people are often a bit nervous, installers a bit nervous about initially using a mega on electronic equipment. They think of a module as electronic equipment, but these are actually tested to thousands of volts.
Yeah.
I mean, they might be rated at 1500 volts, but they're tested even higher than that, aren't they?
They're rated 1500 volts. We'll be tested slightly above that.
Yeah.
Everything have a tolerance in there. Of course, then you have. Yeah, I got an interesting question yesterday. Are we going to make a 2000 volt module?
Wow.
I think probably not. Because all these other equipment, your isolators, your breakers, your fuses, they still need to catch up on this. We're still not yet. And if it's over 1500 volt, you'll be identified as a high voltage, a medium voltage instead of LV. Then you have a whole set of different regulations.
So our standards for 5033 top out at 1500 volts DC. So once you go beyond that, it's more difficult. It's an engineered solution. And also, as you point out, I mean, the plugs and sockets and the cable are only rated to 1500 volts. So everything has to upgrade.
Yeah. There's another issue with a higher voltage that it hasn't always been industrial standard. Is because of PID. So PID potential induction locks. So that's also degradations. So it also to do with a higher voltage. To have higher potential to lose more powers due to PID, and you will see this especially on those older types.
Yeah, PID was a big problem.
Big problems back then.
Yeah.
So I think from 2014, Jinko being one of the first to introduce anti-PID cells. We don't say PID free.
Yes.
Okay, it's marketing. We say anti-PID. So basically, after test, you're still looking at maybe 1%, 2%. It's very, very little for this new later panel right now. Yeah, so that allow us to go for a higher, voltage level to make the string longer, to make it more economy of at the system level. Yeah.
Is it a linear relationship that PID increases with voltage? Or potential for PID?
They're not fully linear, but there are some.
Right. So there is actually merit in staying a bit lower in the voltage window, not just going, I can do 1000 volts, I can do 1500 volts, I'm going to go there anyway, if you don't need it. So unless you're doing like a utility scale, it's unlikely you need 1500 volts. Your string links wouldn't be such an issue.
Well, ideally, you want to do longer the better, of course.
It's labor.
Right? It's labors and everything, but it's another whole big topic, how to design on utility scale.
Yes, yes.
Yeah, there are limitations as well.
Yep.
But yeah, you're right. But see, the other thing we just think about for N-type is actually very good anti-PID as well.
Right.
So if you look at the PID report, it's actually almost zero. We can also say the PID free, or we can almost say they're PID free, not just the anti-PID.
Yep. Yeah. Can I put my future glasses on here and think where is Jinko going with cell type and beyond N-type? Is there other chemistries you're looking at, other materials?
We're exploring everything.
Yep.
Like even for N-type, there are a couple. They're quite a different pathways, right? So now at the moment we're looking at TOPCon N-type. There are the HJT, HIT. There's different way to do it. Right?
Intrinsic thin film.
Yes. No,
wow.
HJT, HIT.
Yep.
Heterojunctions.
Oh yeah. Heterojunction. Gotcha.
And also IBC. So these other ways.
Yep.
Pathways to having to the future, but we just R&D into a lot of things. But being a manufacturer, we're always looking at the production abilities, right? So not only have theoretical products out there, we're choosing TOPCon is because it's a capability for manufacturing. What TOPCon different to the current PERC, it's adding extra steps into productions. So it's pretty easy transformation from the P-type production lines to N-type. It's just adding 2 extra steps. So it allows us to do both products on the same production lines if we need to.
Right. Yeah. So just explain a bit about TOPCon.
So TOPCon is a tunneling oxidized. Sorry, we need to cut this. Okay, it's a bit too long. Yes,
I'll put it on the screen. Don't you worry.
We need to put it on later.
Wow. So TOPCon's the kind of the next step after PERC. But Jinko's not doing it yet, but it's in the R&D phase.
No, sorry. TOPCon is the one we choose. So after, not after PERC, but P-type PERC is one pathway.
Yep.
So N-type, there's a couple pathways.
Yep.
There's TOPCon, there's HJT, heterojunctions. So Jinko is choosing TOPCon as the second generation of N-type.
Gotcha. Well, Dan, that's been really fascinating. One of the things I love doing these interviews is I learn so much, and I've already learned a whole lot about the detailed inside workings of a solar module, but also what Jinko have done. And we haven't really mentioned much about Jinko other than the name. I mean, Jinko's enormous. How do you sit in the market?
We're doing quite well in Australia, globally. So Jinko is the first one to hit 100 gigawatts of global shipment. We're the first to do it. We're being number one for long times, for many years, and we've been PVEL, top qualities for 7 years in a row now. So this is very, qualities and R&D is very focusing on looking at. Market-wise, in Australia, we're I think around 16% for the rooftop domestic, and we have quite successful in the big projects as well. Yeah, I think we're delivering around 2 gigawatts of projects already.
Right. And how long has Jinko been manufacturing solar modules for?
I think it's around 10 years. So the Australia companies has been here around 10 years.
Yes.
I've been with Jinko for 4 years now, and quite enjoying having here because we do have varieties of customers, from 5 kilowatt to 500 megawatts. Yeah, it's pretty crazy. You have talking about one panel's 400 watts, and you're talking about 500 megawatts the second day. So it's quite interesting.
Keeps you on your toes.
Keep your toes. Like design a 5 kilowatts to like helping customer to design like a whole rows of big projects. Yeah,
Great.
Pretty amazing.
Cool. Well, thanks very much, Dan.
Thank you very much.
Okay.
Anytime.